Good morning friends. Now I am going to discuss about routing properties and metrics of 3ASL topology. Based on the network model and satellite indexing scheme, this section derives the key routing properties of 3ASL topology, which is similar but unique compared to 4ASL topology. Most of the differences are due to the vertical data caused by the intermittently missing interplane ISLs. Key routing metrics are derived, including minimum hop count, network diameter, network cost, and average path distance. Minimum hop count between two nodes. First, takes the transmission hop count as the first, this article takes the transmission hop count as the primary routing metric to be minimized rather than the physical distance, which is also a common practice. In addition, the article uses the minimum hop count as the main metric for evaluating the path distance between any two satellites. The figure 4 shows the this diagram shows the shortest path from SC to SD in the 3ASL topology. Extra hops are required compared to the unpruned 4ASL topology, which is indicated by the dashed path. The diagram shows the shortest path from source satellite to destination in the 3ASL topology. The path consists of several interplane and intraplane hopes. The required interplane hopes depend on the orbital plane difference. However, the intraplane hopes are caused by both the satellite index difference and the interplane hopes. When the interplane hopes are required but the corresponding interplane ISL is pruned, a jitter is caused and the extraplane hopes are involved compared to the unpruned 4 ISL topology. Moreover, we notice that the involved extra hopes also depend on the parity of the end nodes. Lemma 1 in 3ASL topology, n interplane hopes involve at least n intraplane hopes. N in NINV between the satellite V1, H1. V2, H2 can be given as follows. NINV equal to n plus H2 minus H1 divided by H2 minus H1 into modulus of H2 minus H1 into modulus of H1 plus V1, 2 minus modulus of H2 plus V2, 2. Proof. Since the interplane ISLs are alternatively pruned and each node has only one interplane Since the interplane ISLs are alternatively pruned and each node has only one interplane ISL, and interplane hope must be followed by a intraplane hope. When V1, H1 when V1, H1, V2, H2 are both even and odd nodes, n interplane hopes involve at least n intraplane hopes. Assume H2 is greater than H1 when V1, H1 is odd and V2, H2 is even. An extra intraplane hope is required while V1, H1 and is even and V2, H2 is odd. One intraplane hope can be saved and at least n minus 1 interplane hooks are required. When H2 is less than H1, a similar conclusion can be obtained and is obtained. Equation 1 is obtained. According to lemma 1, the minimum involved extra plane hooks NINV equal to n or n plus or minus 1, which depends on the type of end satellite. It also indicates that in the 3-axial topology, the more orbital planes are involved, the more intraplane hooks are required. Next, the minimum hop count of 3-axial topology is derived in mesh and torus respectively. 3-axial mesh topology. Hop count in a 3-axial mesh. In a 3-axial mesh, the minimum hop count between the satellite V1, H1 and V2, H2 is as follows. H power 3m is equal to max function of V2 minus V1, H2 minus H1 plus H2 minus H1 divided by H2 minus H1 into OE plus H2 minus H1, where OE is equal to modulus of H1 plus V1, 2 minus modulus of H2 plus V2, 2. Proof. The minimum hop count is the sum of interplane hop count and intraplane hop count. Similar to the 4-axial mesh topology, HH equal to H2 minus H1 when V2 minus V1 is less than or equal to H2 minus H1. The minimum HV is also similar. HV is equal to V2 minus V1. However, when V2 minus V1 is less than H2 minus H1, according to lemma 1, the extra interplane hooks HINV caused by interplane hooks can be greater than V2 minus V1. Therefore, HV should be max function of V2 minus V1, HINV. The combining an equation 1 and the above formula with the total hop count calculation, equation 2 can be obtained. Thank you. Remaining will be seen next class.